minimum oxidation states is shown by the ones in which only the 4s electrons are involved. Okay, another one is unpaired electrons in d orbitals. Just the oxidation state will be given Ti3 plus or Ti4 plus is more stable. So you should be knowing the electronic configuration. So if you have a D0, D5 or D10 configuration, then you can determine that yes, it is going to be extra stable. After manganese you have iron, right? So there again the number of unpaired electrons is going to decrease. Hello everyone, this is Ampli Unnikrishnan from the Department of Chemistry. So today I am back with session 3 of the chapter D and F block elements. So in the last session we have discussed the general characteristics of transition elements, wherein we discussed atomic radii, ionic radii and density, as well as strengths and physical properties, that is metallic character and ionization enthalpy we have discussed. So in today's session we are going to discuss oxidation state, that is the trends in oxidation state and what is oxidation state. Then we'll discuss magnetic properties, formation of colored compounds, catalytic properties, formation of interstitial compounds and alloy formation, by which we'll come to an end to the discussion of the various properties of the D block elements, right? So all of these are important, which can come in your question paper in the form of MCQ as well, right? So beginning with the first one, that is strengths and properties of transition metal of first series, that is a 3D series. So we have already completed ionization enthalpy as well as the metallic character. Now we are going to deal with oxidation state. So you're already familiar with this oxidation state, right? So let's see, all these elements except the last member exhibit variable oxidation state. So the beauty of D block elements is that they exhibit variable oxidation state. It's not just that they have one single oxidation state, they have n number of oxidation state. All these elements being metals give only positive oxidation state. So that is another point to remember. They only show positive oxidation states because they are ready to lose their electrons, right? They are metals, so they will show positive oxidation state. The reason for giving different oxidation state is as follow. Now the question can arise, why D block elements generally exhibit a lot of oxidation states? So the answer is here. The energy difference between 4s electrons and 3D electrons is small, okay? Hence, 3D electrons require little energy to get promoted to the valence shell. As such, they can be easily promoted to the valence shell. Therefore, they are also involved in bonding. For example, I am writing argon 3D 2 4s2. Okay, so this is the electronic configuration of titanium, right? So here you can see you have 3D orbital as well as 4s orbital. So what is said here, why they are showing variable oxidation state is because the 3D electrons and 4s electrons are having very little energy difference. So what happens, the 3D electrons can easily jump into the 4s electron, which is the valence shell, and thereby these 3D electrons can also take part in the bond formation. That is why they are able to show oxidation states, right? Now, the oxidation states of the elements depend upon, first one is number of electrons present in the outermost shell. Outermost shell is 4s, right? Outermost shell is 4s, but the last electron moves into the 3D orbital, right? So the first reason is number of electrons present in the outermost shell, that is in the 4s, and number of unpaired electrons in D orbital, that is the penultimate shell. Penultimate means just before the last shell, right? Last one is 4s, just before that you have 3D. That is why it is called penultimate shell, that is 3D, or else n-1D. I hope it is clear. The minimum oxidation state is given when only 4s electrons are involved in bonding, while the maximum oxidation state is given when all 4s electrons and all unpaired electrons in 3D are involved. So what does that mean? Which are the factors which is contributing to the n number of oxidation states of D orbital? That is, one is because of the presence of electrons in 4s and another one is in 3D. So minimum oxidation states is shown by the ones in which only the 4s electrons are involved. Okay. Another one is unpaired electrons in D orbitals. So if the 4s electrons is completely filled, right, the 4s orbital is completely filled, as well as the 3D has all the unpaired electrons, then we can say that it is having maximum number of oxidation state. Hence, minimum oxidation state will be number of electrons in 4s. Okay, any element, the minimum number of oxidation state that it can have will be the number of 4s electrons will be present, right? If it is 4s1, right, you can say 1 will be the oxidation state, that is a minimum one, right? Now maximum will be how many number of unpaired electrons are there in 3D plus the total number of electrons present in 4s, right? So that will be the maximum. So I hope you are able to calculate the minimum number of oxidation state and maximum number of oxidation states for each of the element present in the 3D series, that is scandium, titanium, vanadium, chromium, manganese ion, cobalt, nickel, copper and zinc, right? Now all these elements contain 2 electrons in 4s, hence they all give a common minimum oxidation state of +2 except chromium and copper, for which minimum oxidation state is +1. So it is an important point to remember, all the elements, the minimum oxidation state is +2 except copper and chromium, which is only showing +1 oxidation state. Why is that? Because the general configuration you also know, it is argon, it can be 3D1, 3D2, 3D4, 3D5, right? And so for example, if I am adding 3D3 and you have 4s2, so always in your final shell there will be 2 electrons, right? So that means minimum oxidation state will be always 2. Maximum can be dependent on the number of unpaired electrons present in 3D. So for example, if I am writing the electronic configuration of chromium, it will be argon 3D5 4s1. See, in that case you can see minimum oxidation number will be +1. So I hope the difference is clear for you. So you can see here itself, for scandium, you have 3D1 4s2. This is argon 3D1 4s2. So the total or the maximum number of oxidation state it can have, you have 4s2 and 3D1. So it can have +3 oxidation state. Now coming on to titanium, it can have +2, +3, +4. Now vanadium +2, +3, +4 and +5. So you already know how to calculate this. Now moving on to chromium, it can have +2, +3, +4, +5 and +6. Because totally there are a total of 6 electrons which is present here. All these 6 electrons can be donated, right? Now iron +2, +3, +4 and +6. Cobalt you have +2, +3 and +4. Nickel you have +2, +3, +4. Copper you have +1 and +2, and zinc you will have +2 only, because it is completely filled, so it is only ready to lose the 2 electrons, right? So this is the order which you can see. From here itself you can observe towards the end the oxidation numbers are less, and towards the middle the oxidation numbers are more, and manganese is the one which is having the highest number of oxidation state. It ranges from +2 to +7, right? Moving on, the relative stabilities of various oxidation states of a given element can be explained on the basis of rule of extra stability, according to which D0, D5, D10 configurations have stable configuration. So you also know that the relative stability of various oxidation states. So we have just learned various oxidation state, that is +2, +3, +4, right? Now what or how can we determine which oxidation state is more stable for an element? It depends upon the electronic configuration itself. If the electronic configuration involves D0, D5, D10, this means no d electrons itself. Here you have half-filled d orbitals, here you have fully filled d orbitals. So we already know if it is half-filled or completely filled, they will have extra stability. That means that particular oxidation state will be more stable. I hope it is clear. Now hence the ions which have these configurations are more stable. For example, the stability order of some ions which is shown here. So you have titanium 4+ and titanium 3+. So comparing the electronic configuration. So generally what is the electronic configuration of titanium? It is argon 3D to 4s2. Now what if it is titanium 3+? You will have argon, 2 electrons from the 4s and 1 from 3D will go, and you will have 3D1. So 4s will be 0. And if it is titanium 4+, you will have argon, all the 4 will be gone. So 3D 0, 4s 0. So now can you observe titanium 3+ and 4+ oxidation state I am comparing. Here 3D1 is there, here it is 3D 0. So you can see here there are no d electrons, so it is having extra stability. So the question will be like, which is more stable? Okay, so just the oxidation state will be given. Ti3+ or Ti4+ is more stable. So you should be knowing the electronic configuration. So if you have a D0, D5 or D10 configuration, then you can determine that yes, it is going to be extra stable, right? So Ti3+ means 2 electrons from here and 1 from here will go. 4+ means 2 and 2, all the 4 will go. So it is completely not available. Now manganese, Mn2+, it will be 3D5 4s0 and Mn3+ is 3D4 4s0. So from here itself you can see you have 3D5 and 3D4. Which one will be more stable? Of course, 3D5 will be stable. Now coming on to iron, Fe3+ and Fe2+. Fe3+ will be 3D5 and Fe2 plus is 3d6. Of course, Fe3 plus is going to be more stable. So you can expect questions in this form as well, right? Now moving on to the next property, that is magnetic property. Right. So this is also an important part from which you can expect questions. So we have completed oxidation state. Moving on to the next one, that is magnetic property. The paramagnetic nature is due to the presence of unpaired electrons. The magnetic moment of an atom or ion can be calculated using this particular equation. So you already know the magnetic property. It can be either diamagnetic or paramagnetic. We say the element is paramagnetic if there is presence of unpaired electrons. If all the electrons are paired, then it becomes diamagnetic. Now the extent of paramagnetism can be calculated using this particular equation, that is mu. The magnetic moment is equal to root of n into n plus 2. And you can see Bm is the unit which is Bohr magneton, root of n into n plus 2. Now what is this n? N stands for the number of unpaired electrons, right? It tells us about the extent of paramagnetism. So n is the number of unpaired electrons, right? Thus magnetic moment increases with the increase in the number of unpaired electrons. Hence, the observed magnetic moment is useful to know the number of unpaired electrons present in an atom or ion. That means what? If we know if we are able to calculate the magnetic moment of a particular element, and if it is a high value, we can tell that that particular element is having a greater number of unpaired electrons, because greater the number of unpaired electrons, greater will be the magnetic moment value. I hope it is clear, right? In the first transition series, as the atomic number increases from 21 to 25, that is from scandium to manganese, right? The number of unpaired electrons in 3D increases from 1 to 5, and hence the magnetic moment or paramagnetic character increases and becomes maximum at manganese, right? You have 3D1 for scandium, then you have titanium which is 3D2, vanadium 3D3, and you have chromium which is 3D5, and manganese it is 3D5, right? So till manganese, what is happening? The unpaired or the number of unpaired electrons is increasing from 1 to 5, right? Now, however, thereafter the number of unpaired electrons will decrease. Right. So after manganese, you have iron, right? So there again, the number of unpaired electrons is going to decrease. Why? So for iron, what is the electronic configuration? It is argon 3d6 4s2. So what is the number of unpaired electrons you are having? See, 3d6 means 1, 2, 3, 4. 1, 2, 3, 4, 5. You have 1, 2, 3, 4, 5, 6. See, again you can see only 4 number of unpaired electrons is there. So again it is going to decrease from iron to the end. So you can see here the number of unpaired electrons will decrease with the increase in atomic number. As such, the paramagnetic character will decrease. At zinc, that is the last one, that is 3d10. The number of unpaired electrons is 0, and hence zinc is diamagnetic in nature. What is zinc's electronic configuration? It is argon 3d 10 and 4s2. So it is completely filled. So it is diamagnetic. So I hope it is clear. Right. So let's calculate the magnetic moment of certain elements. So you can see it is cobalt 2 plus. Okay. So how do you calculate for cobalt? The atomic number is 27. So how do you write? It is argon. It is argon 3d7 4s2. Right. You can see here 1, 2, 3, 4, 5, 6, 7. 7 and 4s2. Now the question asks you for 2 plus. So 2 electrons are going to move from the 4s orbital. It is going to be removed. So what happens? It will become 4s0. Now electrons in 4s orbital. You have 1, 2, 3, 4, 5, 6, 7. Right, 7 electrons are there. So now we have to calculate the number of unpaired electrons. These two are paired, these two are paired. So you have 1, 2, 3. 3 unpaired electrons. So the value of n is 3. So you calculate root of n into n plus 2. That is root of 3 into 3 plus 2. 3 into 3 plus 2 is 5. 5 into 3 is 15. You have root 15, which is 3.87. Bohr magneton, right? Thus the value will be 3.87. So I hope it is clear. This is how you have to calculate. So for the element at ground state, we need to know. And then in the excited state, that is 2 plus or 3 plus, we have to write the electronic configuration and then check the number of unpaired electrons. Now the next one, Fe2 plus iron, the atomic number is 26. So it will be argon 3d6 4s2. So you have 1, 2, 3, 4, 5, 6 and 4s2 you are having. So it is asked in 2 plus state. So the 2 electrons from 4s orbital will be removed, right? So you have now 4s0. Now, how many electrons are there? 1, 2, 3, 4, 5, 6, right? Out of this, how many unpaired electrons are there? You have 1, 2, 3 and 4. So, what is the value of n? It will be 4. So, you can see here root of 4 into 4 plus 2 and finally it will be 4.90 Bohr magneton. So, I hope it is clear. Right. Now, moving on to the next one, that is formation of colored compounds. So, D block elements have the ability to form colored compounds. Now, what is the reason behind it? We are going to study here. So, in your lab also, you have observed that the manganese salts, the iron salts, all of these are colored, which we do not generally keep for the experiment or the salt analysis experiment, right? Because all these manganese, iron and all of that, that is copper also, it all comes under the D block elements. So, they all have the ability to show colored compounds. That is, manganese will be a pink colored salt, very, very light pink color salt. Iron will form green colored salt. Copper will form blue colored salt. Now, what is the reason behind forming all these colored complexes? Let us see. Most of the compounds of transition metals are colored in the solid state or in its solution. The color of a compound is due to its property to absorb light of a certain wavelength from the region of visible part of electromagnetic spectrum. The actual color of the substance depends upon the wavelength or color which it absorbs from white light. The color of the transmitted or reflected light is the color of the substance. It is complementary of the color which absorbs the substance. So, what does it mean is, if you are able to see a color in that particular compound, it is because it is absorbing a particular wavelength from the visible light. That is, the D block elements have the ability to absorb certain wavelengths of light from the visible region, and whichever it is absorbing, okay, for example, if it is absorbing the orange color, okay, if the D block element is absorbing a wavelength which is equal to the wavelength of the orange color, the complementary color will be the one which is shown by the substance. Okay, if it is absorbing orange color, the color which is shown will be the complementary one, that will be blue. If it is absorbing yellow color, then the color which is shown in the solution will be violet. So, what you have to understand, if the solution, for example, if the solution is violet in color, that does not mean that the D block element has absorbed violet range of the visible light. It has absorbed the wavelength of yellow. Okay, so it is always complementary to each other. This is what you have to remember. Now, the next one is transition metal ions containing unpaired electrons or vacant d orbitals are therefore colored. Now, the ones which are having unpaired d electrons, they will only show a color. That means your zinc, cadmium, mercury, that belongs to the last set, that is 3d10. They are having 3d10 in their electronic configuration. They don't have unpaired electrons. Hence, they do not show color. Right, only the ones which is having unpaired electrons. So, vacant d orbitals or unpaired electrons should be present, then only they will show color. Right, naturally the transition metal ions which have completely filled d orbitals, that is no unpaired electrons, are colorless. You can take the example of zinc also, they are colorless. The ions which have completely filled d orbitals, that is 3d10, are colorless. Zinc 2 plus, copper plus, all of them are colorless because they have a 3d10 configuration. I hope it is clear. So, what is the important factor? It has to be unpaired electrons should be present, and it at least you should have vacant d orbitals. Now, cuprous ion, that is Cu plus, has 3d10 configuration, hence it is colorless. But cupric ion, it is Cu2 plus. So, Cu plus it is 3d10, but Cu2 plus it will be 3d9. So, what is happening? One more electron is lost. So, in that case, it will have unpaired electrons, right? So, 3d9 configuration and contains one unpair of electron. As such, it is colored, that is blue color it will show. Hence, cupric salts are blue in color, while cuprous salts are colorless, right? Cu plus will be colorless, Cu2 plus is colored because of the presence of unpaired electrons. So, I hope the factors is clear for you. It should have vacant d orbitals or else it should have unpaired electrons. I hope it is clear, right? You can see here itself, scandium 3 plus, it is 3d0 electronic configuration. So, of course, it is going to be colorless, right? No unpaired electrons, it is 3d0. Titanium 4 plus also 3d0, it is going to be colorless. Now, titanium 3 plus, it is 3d1. One unpaired electron. So, of course, it is showing color, it will show purple color. Vanadium 3 plus, it will show green color because there are two unpaired electrons. Chromium 3 plus, 3 unpaired electrons, violet color. Mn 3 plus, manganese 3 plus, it will also show violet color. Manganese, Yes, you can see 5 unpaired electrons. It will show a baby pink color. Now Fe2 plus and Fe3 plus, both of them are having unpaired electrons. It will show green and yellow color respectively. Right. Now you have cobalt 2 plus, you have pink color. Nickel 2 plus you have green color, copper 2 plus you have blue color, and Cu plus and Zn 2 plus will be colorless because there are no presence of unpaired electrons. I hope it is clear. Now you can see the color also here. Titanium 3 plus, it will be a purple color. Vanadium, it can show plus 2, plus 3, plus 4 and plus 5 oxidation state. Right. Chromium, it can show plus 2, plus 3 and plus 6. So in each of this oxidation state, the color shown by the ion will be different also. Right. You can see manganese plus 2 and plus 7. The color difference you can see here. Iron, it is plus 2 and plus 3. Right. Cobalt plus 2. Nickel plus 2 and copper plus 2. It is blue in color. So I hope the color shown by the compounds is clear for you. So this is how D block elements will show colored compounds. Now next one is catalytic properties. So as D block elements are also used as catalyst in various reactions. So you are already familiar with what is catalyst. Catalyst is a substance which is generally used to increase the speed of the reaction. It will take part in the reaction and towards the end of the reaction we will obtain it back as it is itself, right? So most of the transition metals and their compounds have good catalytic properties. Their catalytic properties are considered due to the following reasons. So this is an important question. Why D block elements are used as catalyst? Okay, so the first reason is, according to modern theory of catalysis, catalyst forms an intermediate which is unstable compound with reactants. This intermediate compound readily decomposes to give the product and the catalyst is regenerated. On account of their variable oxidation state, transition metals form unstable intermediate compound readily. Okay, so how do the catalyst work? It will form unstable compounds with the reactants first. Then it will immediately decompose and form the products. So D block elements have the ability to form unstable compounds or unstable transition compounds so that it can easily decompose. So that is the reason, because they are having variable oxidation state. It is having variable oxidation state, so it can easily form a transition compound and it can directly decompose easily as well. I hope it is clear. Another one is, these elements can provide large surface area for the reactants to be absorbed side by side. This helps the reaction to occur on the surface of the catalyst. So these are the two reasons. Another reason is, it is providing a large surface area, so it can act as a catalyst. Now few examples are iron, which is used in Haber process for the manufacture of ammonia. So iron is a D block element, right? Where it is used, you have to remember. Next one is nickel, which is used in hydrogenation of oils and unsaturated hydrocarbons. Next one is vanadium pentoxide, V2O5, in oxidation of SO2 to SO3 and in the manufacture of sulfuric acid by contact process. So these are few examples of D block elements used as catalyst. So the reason why they are used as catalyst is what you have to remember. One is they provide large surface area. Another one is that it can easily provide or produce a intermediate state which can readily be decomposed, right? Now the next one is formation of interstitial compounds, right? So interstitial compounds are those which are formed when small atoms like hydrogen, carbon or nitrogen are trapped inside the crystal lattices of transition metals. So you have metals which will be arranged in a very compact order, right? So what will happen is there in that crystal lattice? You can see here, this is a lattice which is set up here. So in this crystal lattice, you can see some gaps here, right? These are the pink balls, you can see those are the metals, and there are some interstitial gaps that you can see in between these metals. So these are the interstitial compounds which is formed between the interstitial spots of these metals, right? So they are non-stoichiometric and are neither typically ionic or covalent. These interstitial compounds have similar chemical properties as the parent metals but different appreciable in their physical properties such as density, melting point, hardness, etc. So they will have properties similar to that of their parents, but it will be quite different based on their melting point and density, right? Interstitial compounds are hard and denser. This is because smaller atoms of lighter elements occupy the interstices in the lattice, leading to more closely packed structure. Due to greater electronic interaction, strength of the metallic bond also increases. So interstitial compounds, D block elements, are able to form because the hydrogen, carbon or nitrogen, these small atoms will occupy the interstitial positions. So what will happen? Now if these interstitial positions are also being occupied, they are more tightly packed. So in that case, what will happen? The melting point will increase, or what happens? It becomes denser and more harder. So that is how interstitial compounds is formed. That is, in the interstitial positions, the small atoms will come and occupy. Right. Fine. Now they retain metallic conductivity. Example is TiC, Mn4 and Fe3H. All of these are examples of interstitial compounds. Right. Now last one is alloy formation. Now what are alloys? It is a mixture of metals. Right. They have various applications also in our day-to-day life. Transition metals form a large number of alloys. Alloys are formed by the metals whose atomic radii are smaller. So 3D series elements are quite similar in atomic size. We already know that they are quite similar in their atomic size and other characteristics. Hence, the atoms of one metal can substitute the other atoms of other metal in a crystal lattice. Right. Thus, on cooling the molten mixture of two or more transition elements, solid alloys are formed. So, all of these are having almost a similar size and characteristics. So, what can happen? These 3D elements can be combined one over the other, and a mixture of these elements or mixture of these metals can be formed. So, it is cooled together. So, we will get a alloy, which is a mixture of different elements. Right. For example, chromium, vanadium, manganese, nickel, etc. are used with iron to form variety of steels and stainless steel. Okay, steel and stainless steel, iron is combined with any of those metals. Now, alloy, the brass, which is a mixture of copper and zinc. So, copper zinc alloy is called as brass. Now, you have bronze, which is copper tin alloy, and are also considerable importance. So, all of this you can remember. Few examples of various alloys. So, it's basically a mixture of alloys. Now, why D block elements are able to form alloys? It is because of their smaller size and they are all comparable with each other. Right. Now, in the next session, we are going to study the preparation of potassium dichromate, and thereby we'll study the preparation of potassium permanganate also, and then we'll move on to actinoids. So I hope the concepts that I've covered in this session is clear for you. So that's all for today. Thank you.